Hi everybody, I hope this video finds you well. In this video we're going to be following up the sort of previous investigation of determining if a matrix has an inverse and the sort of relations to the rank of a matrix and how the rank of the matrix sort of tells us about whether or not an inverse will exist. In this video, we're actually going to investigate computationally how you would actually determine the inverse to a matrix. Not just about whether or not it'll exist, but actually how do you find that inverse if it does exist. So we're going to talk a little bit about finding the inverse to a matrix and then take a look at a couple examples here. So you should sort of recall the main idea of the sort of previous proof, right? We sort of said that if A has an inverse, we called it sort of A with that little -1 as our notation. So if A has an inverse, then we can define this inverse as A inverse equals this group of sort of column vectors, x1, x2 down to xn, with AXK equal to EK. And remember, these EKs were those elementary sort of column vectors, and these guys actually were the column vector components of the identity matrix. And this was sort of the trick that we use. We define the inverse, if it's going to exist, as the sort of solutions to the coefficient matrix times those solutions equaling the sort of identity matrix, the column vector components of the identity matrix. And the idea was then, if you imagine actually taking A times that A inverse, what ends up happening is A multiplies onto each of these columns, resulting in these elementary column vectors, which then make up the identity matrix. So this means we can actually use this to sort of determine how we're going to find the inverse in general of a matrix. So what this sort of means computationally, we can solve all these systems simultaneously. So we can actually do this at the same time, these systems at the same time here. So instead of having to go through manually and do, okay, A times x1 equals E1 and then AX2 equals E2 and doing that over and over again, we can do them sort of all at the same time. What that sort of means is that what you guys will do is you will start with your matrix A and you will adjoin to it not a single sort of column vector. You won't augment with a single column vector. You'll actually augment with the entire identity matrix. So over here, you'll have your original matrix, and over here, you will have all of the columns of the identity matrix. So each of these columns, of course, correspond to one of the elementary column vectors. Then you will use elementary row operations to change this side into the identity matrix. So you'll take this and you'll do elementary row operations until it looks like the identity. What happens on the other side will actually become your inverse matrix. Now, as you do this, if it is impossible to use elementary row operations to go from A to the identity, then A inverse does not exist. And if you think about it, that should make sense, because if you are unable to take A via elementary row operations to the identity, then that means that the rank of A is not equal to n, because at some point when you're doing those elementary row operations to A, you'll get a 0 row, which means that it doesn't have full rank, and from our previous sort of theorem, we know that that means that the inverse doesn't exist. So computationally, this is a very simple way, even though it'll be sort of arithmetically time consuming, there will be a lot of computations to do, but it's a very simple idea. You take your original matrix, you augment it with the entire identity matrix, you use elementary row operations to change that into the identity matrix on the left-hand side. What happens on that right-hand side will then be your inverse. If you find that it is impossible, along the way you get a 0 row as you are taking A and trying to make it look like the identity, well, that means that A inverse does not exist, and it also tells you it does not have full rank. So for the remainder of this video, we're just going to look at a couple examples of going through and doing this. So let's go ahead and get started with our first one. So we've got a square matrix here. A is going to be the matrix 1, 3, 0, negative 1, 2, 5, 2, 1, 1. And we want to try to find the inverse of the following matrix if it exists. And notice that that's going to usually be the sort of statement in there, right? Not every matrix has an inverse, right? So we are always going to have that sort of thing of finding the inverse if it exists. So let's see how to do this. We're going to start by taking this matrix 1, 3, 0, negative 1, 2, 5, 2, 1, 1, and we're going to augment it with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, so our goal now is to take this left-hand side and make it look like the identity matrix. So we sort of like that we've got that leading 1 there. I mean, we might as well just sort of follow our general rules for going to row echelon form and then move it into reduced row echelon form, which will be the identity if possible. So we can use this guy to sort of clear out the things below it. So we'll go ahead and do sort of 2 operations here. We'll take row 2 and we'll replace row 2 with row 2 plus row 1. And we can take row 3 and replace row 3 with row 3 minus 2 row 1. Again, remember whenever you do that sort of third elementary row operation, make sure that this matches the first component there, right? You've got to use the same row as the one you're replacing, and then you can use any modification of a different row. So if we do that, what should we get there? Well, the top is going to remain the same, 1, 3, 0, and then of course 1, 0, 0. Then we took row 2 and added row 1 to it. So that should give us over here 0, 5, 5. And then of course we're adding this row onto this row as well. So we should get 1, 1, 0. All right, then we also are taking row 3 and subtracting to row 1. So that looks like we should get a 0 there. Then 1 minus 6, so that's going to be negative 5. And then 1 minus 0, which is going to be 1. And then finally, we get 0, 0, 1 minus that 2 row 1. So it looks like we should get a negative 2, 0, 1 there. All right, so that's our sort of start of this operation. So this is looking good because all that stuff is sort of zeroed out there. Now we've got some options. We could go ahead and multiply this row by 1/5, but we might as well just use this guy right away to clear out the minus 5 below. It's sort of convenient that there's both 5s, so let's just go ahead and do that. So let's go ahead and take row 3 and replace it with row 3 plus row 2. That's just, again, that's not maybe the algorithmic way, but it's sort of smart that we can do that. So if we do that, we get 1, 3, 0, and then of course 1, 0, 0, that's not being affected, 0, 5, 5, 1, 1, 0, that's not affected, and the other one should be 0, 0, 6, because we're adding on there, and then it looks like we should get negative 1, 1, 1 when we do that, and adding, of course, this 1, 1, 0 to that negative 2, 0, 1. Okay, so there's our new matrix there. Let's go ahead and see what we should do next there. Next, it probably is a good idea to go ahead and make those, divide through by 5 and divide this guy by 6. So let's go ahead and do those simultaneously. We'll do 1/5 row 2 and 1/6 row 3. So it'll be a little ugly because we'll start getting fractions, but that's okay. 1, 3, 0, 1, 0, 0, nothing done there. Then it looks like we're going to have 0, 1, 1, and then 1/5, 1/5, 0. And then we're going to have 0, 0, 1, negative 1, 6, 1, 6, 1, 6. Okay, so this is looking good. At this point, we actually know something important. At this point, you've put this into row echelon form. It's not the same as the identity matrix. It's not in reduced row echelon form, but it is in row echelon form. That means you can tell right here that the rank of A is 3. So the rank is full. It matches the rows and columns. That means there will be an inverse. So right here, we should sort of make a little note, right? Rank of A is 3. So we can tell that right at this sort of stage, and that means that we know that we will be able to find an inverse. All right, let's continue on finding that inverse, right? Now we'd like to start clearing out the things here and here. So we can do that however we sort of like. I'll go ahead and just clear out this guy sort of first, sort of using this to clear out anything above, sort of doing like a back substitution. So let's go ahead and do that. We're going to have to take row 2 and replace it with row 2 minus row 3. So if we do that, we have 1, 3, 0. Nothing's changed there. 1, 0, 0. 0. Now we're subtracting 0, 0, 1. So we get 0, 1, 0. It'll be a little bit messy because we're going to have to combine these 1/5 and these 1/6 here. But of course, we know that that's just going to be in 30ths. So I guess that'll be what? 6 over 30 minus 5 over 30. So that sounds like 11 over 30. So that'll be 11 over 30. Then we've got a 6 over 30, sort of minus a 5 over 30. So that sounds like 1 over 30. And then 0 minus that 1/6 sounds like negative 1/6 there. And then we have 0, 0, 1. And we've got negative 1/6, 1/6, and 1/6. Okay. Last thing we need to do is just get rid of this guy here. So we should go ahead and do one more sort of replacement. We'll need to take row 1 and replace it with row 1 minus, what is that going to be? 3 row 2. So when we do that, we should get 1, 0, 0. A little bit messy here, but we're going to take 1 and subtract by 3 times 11 over 30, which sounds like 11 over 10. So that'll be 10 over 10 minus 11 over 10. Sounds like minus 1/10. Then we've got sort of 0 minus 3 times 1 over 30. So that sounds like minus 1/10 as well. Minus 1/10. You know what? I think that's a little ugly. So let's just go ahead and pop this guy onto the next sort of line there. So we'll pop this guy down here. So we're getting 1, 0, 1. Oh, sorry. 1, 0, 0. 1, 0, 0. And we were doing this row minus 3 times this guy. So the first one was 10 over 10 minus 11 over 10. So that was negative 1/10. Then 0 minus 1/10, which was minus 1/10. And then 0 plus 1/2, so that'll be 1/2 there. And then we had 0, 1, 0, 11 over 30, 1 over 30 minus 1/6, 0, 0, 1, minus 1/6, 1/6, 1/6. So this tells us that A inverse here is actually minus 1/10, minus 1/10, 1/2, 11 over 30, 1 over 30 minus 1/6, minus 1/6, 1/6, 1/6. So there is our inverse there. Can we sort of check this? Well, we could, right? We could actually sort of confirm if we do A inverse. Let's just make a note that this is going to be a check here. Not necessary if we're comfortable with the process, but we can do a quick check. If we take A and we do 1, 3, 0, minus 1, 2, 5, 2, 1, 1, and we multiply it with our inverse, minus 1/10, minus 1/10, 1/2, 11. I feel like we should probably do this on a separate page. Yeah, that's probably a good idea. All right, so what we'll do is we'll just go ahead and add an extra page on here. So let's go ahead and do that. All right, so we can do a quick check with this, right? So remember our A matrix that we originally had here was 1, 3, 0, negative 1, 2, 5, 2, 1, 1. And our A inverse that we just found, I believe was negative 1/10, negative 1/10, 1/2. And then 11 over 30, 1 over 30, and negative 1/6, and then finally we had negative 1/6, 1/6, and 1/6. So we can actually just check A inverse. That is going to be 1, 3, 0, negative 1, 2, 5, 2, 1, 1. Then times our claimed inverse, negative 1/10, negative 1/10, 1/2. 11 over 30, 1 over 30, negative 1/6. Negative 1/6, 1/6, 1/6. So let's just check. We take this row. Oh, My apologies there. Then we take this row times this column. If we do that, it looks like we should get negative 1/10. Then we should get 11/10. So negative 1/10 and 11/10. That sounds like 1. Then we can take this row times this column. We should get negative 1/10 and 1/10. So that would be 0. And then we can take this row times this column. Looks like we should get 1/2 and negative 1/2. So that would be 0. Then we take this row times this column. Looks like we should get 1/10 and 11/15 and negative 5/6. So that's a little complex, right? But we can sort of just write that out, right? That we said we should get 1/10 plus 11 over 15 minus 5 over 6. Sort of horrendous with fractions, but whatever, right? We're all good with that. So we should get 22 over here. That should be a 30 over 30, and then minus, 25 over 30. And, we can definitely see that that's going to be 0. Then we can take this row times this column. It looks like for that guy, we should get like a 1/10 plus a 1/15 plus a 5/6. So we do the same sort of thing. We make that 3 over 30, 2 over 30, 25 over 30. Yep, that's a 1, so that's nice and easy. This guy here times this here, right? Looks like we should get negative 1/2 minus a 1/3 plus 5/6. Yep, that looks like negative 3/6, negative 2/6 plus 5/6. That is indeed 0. Then we can start with the bottom row, 211 times this whole mess. So if we do that, looks like we should get negative 1/5, 11 over 30, and minus 1/6. Again, we can change all that. That's going to be negative 6 over 30, 11 over 30, and minus 5 over 30. So that is indeed 0. This guy times this row. So it looks like we should get like a negative 1/5 plus a 1/30 plus a 1/6. That looks like negative 6 over 30, 1 over 30, and 5 over 30, right? So there we go, that's 0. And of course, this final row times this column here looks like we should get 1 minus a 6th plus a 6th, which is indeed, we don't even need to write that, do we? It is 1, so we're all good. All right, now, technically, is this our full check? No, right? We should also check, that A inverse A equals IN. But we'll leave that for you guys to sort of do, right? There's not really any need to do this check. Our process will always work. But this is just to confirm, since this was our first example, that, this sort of idea of augmenting with the identity matrix and then doing these elementary row operations really does allow us to go from A to A inverse, right? This is pretty messy in here, so I don't recommend doing this check unless you sort of just want to see for yourself. But do keep in mind that to check something as an inverse right now, we need to show that it multiplies on either side to the identity. All right, let's look at one sort of more example of trying to find the inverse of a matrix. All right, so we've got this matrix here. This matrix is a 4x4 matrix. It's 2, 0, 3, 1, minus 1, 2, 4, 0, 3, 2, 10, 2, 0, 0, 0, 1. And what we're going to try to do with this is, again, try to find the inverse of the matrix if it exists. So we'll start with that augmentation. So we'll do 2, 0, 3, 1, minus 1, 2, 4, 0, 3, 2, 10, 2, 0, 0, 0, 1, and we'll augment with the 4x4 identity, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So we've got lots of operations that we could sort of begin with, right? We're happy with this sort of bottom row down here, so we probably don't want to mess with this. We could start to sort of work with this guy. It might be easier to put this guy up top. So let's go ahead and do that. Let's go ahead and just interchange row 1 and row 2. So if we do that, looks like we should get negative 1, 2, 4, 0, and then of course 0, 1, 0, 0, and then 2, 0, 3, 1, 1, 0, 0, 0, and then everything else stays the same. 3, 2, 10, 2, 0, 0, 1, 0, and 0, 0, 0, 1. and then 0, 0, 0, 1. Okay. So let's go ahead then and start using this guy to clear out the stuff below. Obviously, we could also hit him with -1, but we can always do that later. So let's go ahead and take row 2 and replace it with row 2 plus 2 row 1, and row 3 with row 3 plus 3 row 1. So upon doing that, we should have -1, 2, 4, 0, 0, 1, 0, 0. Then we've got 0, 4, looks like 11, and 1. And then that was 2, so it was 1, 2, 0, 0. And then we've got, looks like 0, and that's going to be 6 and 8. And that's going to be 12 and 22. And that's going to be 2. And then when we add that guy, and it was 3, so it'll be 0, 3, 1, 0. And then, of course, we didn't do anything to the bottom. 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, we can sort of be a little smarter than our algorithm and notice that this guy right here can sort of cancel this guy out entirely. So let's just jump and do that immediately, right? So let's go ahead and do row 3 replaced with row 3 minus 2 row 2. So we're sort of jumping ahead a little bit, but let's go ahead and do that. And that's not going to affect the top one. It's not going to affect the second row either, so we've got that. And then, of course, this is going to zero out that sort of row there. And then, of course, if we do that, it looks like we should get -2, -1, because 3, yep, and then 1 and 0. And then 0, 0, 0, 1, 0, 0, 0, 1. So what does this tell us right here? Well, as soon as we get that 0 row, we can see that it's going to be impossible to actually take this matrix B and put it as using elementary row operations into the identity matrix, right? In other words, since it has a 0 row, we immediately know now that the rank is less than 4, right? It's not going to have full rank because it has at least 1 0 row. So what this tells us, right, from here is this guy, as soon as we see this, this tells us B is not invertible. So in other words, B inverse does not exist. Now, just out of curiosity, are we actually convinced that we know the rank of B? Well, we're not totally in row echelon form, but you should be able to see that we, except for these guys not being leading ones, we are basically in row echelon form. If we multiplied this row by -1, we'd have a 1. If we hit this guy with a 1/4, we'd have a 1. And if we hit this guy, well, he doesn't need to change at all. So we can actually sort of make a note here. We can see that rank of B is equal to 3, not equal to 4. So again, that goes back to that sort of main theorem that we showed from the last video, that if the rank is not full, then there will not be an inverse. So there's 2 computational examples, one where we did successfully find the inverse and did half of the check to see that it really was the inverse, and then a second example that shows you guys what to look for when a matrix is not invertible. We'll have one last video on section 2.6 that'll sort of talk us about how sort of the inverse relates to some of the other properties and operations we've seen on matrices. So we'll take a look at that in the next one.